All right, hope you're doing well. This will be the start of chapter 11, the last chapter for Chem 1B. Hooray! And the topic of this is electrochemistry, which I think is a fascinating area of chemistry and the reason batteries work. And so we'll dive into that a little bit. For now, we'll kind of start with a review of redox chemistry because that's really what electrochemistry is all about. And kind of the mnemonic oil rig with these arrows we use in Chem 1A. You'll want to remember that. It'll be really helpful. And also, as we'll see with talking about oxidizing and reducing agents and electrons transferred, all this stuff will play an important part in this chapter. So at the end of this worksheet, I put a little summary of the oxidation state rules. You can check that out if you want a refresher. And that's what you would want to do in this case to just, if you're given an overall reaction, assign the oxidation states and see what's changing and then you can tell what's oxidized or reduced. So make sure you can do that. I'll assume that you've done that. If not, you can kind of pause and try to do that. So the ones that would be important would be these ones here. Basically, the hydrogens and the oxygens are going to be +1s and -2s respectively, which is usually the case. So I'll just kind of leave those out. But again, make sure you can verify for these ones, the manganese and the sulfur elements in this reaction, they're changing. So once we do that, if we identify the oxidized first, that would be the one that increases its oxidation state. And if we look at these, the one that's doing that is the sulfur. So the H2SO3 would be the substance that's oxidized. Again, it's just kind of the sulfur in that, but we say the whole reagent. And the manganese is decreasing its oxidation state and in this reaction, and then that's going to be what's reduced. The permanganate ion, specifically MnO4- is what we would say is reduced. And if we recall, the thing that's oxidized is the reducing agent. This is that backwards concept, but when you say agent, you're always referring to what it's doing to something else. So the thing that's oxidized itself is reducing something else, hence it's a reducing agent. That's going to be what we go over in the next problem more thoroughly. So we'll touch on that more. The last thing we have in the question is just to do the number of electrons transferred. So if we take sulfur, for example, it's going from +4 to +6 in this reaction. And so it's losing 2 electrons, but this is where we want to keep track of how many there are. There's actually 3 sulfurs in the reaction. So we end up getting 6 electrons that would be lost. And that's going to be the answer for how many electrons are transferred. Because we can do that, or we can look at the manganese. We only really need to look at one side. If you remember from balancing these reactions, you have to have the same number lost and gained in an overall balanced reaction. So if I look at the manganese atom, it gains 3 electrons, but there's 2 manganese atoms in this reaction. So we then want to say, okay, each manganese is gaining 3. There's 2 of them, so that's really a total of 6 electrons. And again, those 2 numbers have to be the same. So we would say, 6 electrons are transferred, right, going from the sulfur to the manganese. Okay, that's a little review, like I said. And now with these next few parts in problem 2, we're going to refer to this standard reduction potential table, which I also put this portion on the end of the worksheet. There's a much bigger table in the book and on Alex. And I would recommend with Alex because you can change the order. It can either be alphabetical or you can change it based on the value. I would do the value like I did here from most positive to most negative. As you'll see, these little shortcut tricks I show you really only work if they're in order of value. The alphabetical one, it's not going to help you unless you're just looking for a certain, letter, like you're looking for copper or something. Then that might help you first find that. But then I'd switch it to the numerical order for any kind of problem involving strength, or is this going to react with this? So before we get to those little tricks, the strongest oxidizing agent, if we remember, is something that's really good at being reduced. So we want something that's good at being reduced, because remember, an oxidizing agent is reduced, right? It's like a towel is a drying agent because the towel gets the water and it dries something else. And a thing that's reduced is oxidizing something else. So what we're looking for is things that are reduced. Now, in all of these tables, they are reduction tables. And that means that everything that's on the left side is by definition being reduced. So all of these species here, just kind of circle them all, are things that are oxidizing agents because these are being reduced. They're gaining electrons, F2 plus electrons or H plus electrons. So these are all things that are being reduced. Reduced species, which are oxidizing agents, okay? One thing I did just notice is that somehow when I was making this table, I must have messed up because these two numbers are actually not in order. That's fine. I don't think I have iron 3+ in any problem. So we can just kind of ignore that one or mentally put it above the H+. Okay, so let's see. Strongest oxidizing agent, good at being reduced. Well, how do we tell it's good at being reduced? That's where the numbers come into play. So we have aluminum 3+. Let's look at the reduction potential for that. Reduction potential of aluminum 3+, if we find that, is going to be negative 1.66. That's not really good at being reduced. That number is negative, which means it doesn't really want to happen. The reduction potential of gold, well, the problem with gold is that gold metal is actually on the wrong side. Gold 3+ would be able to be reduced, but gold metal is not an oxidizing agent. So that's where you have to be careful. This is wrong, right? So basically, I'm going to cross this off. Not oxidizing agent, on the wrong side. Okay, then we have reduction potential of water. You can find that here. Where is water on the left side? Water is actually on both sides, so you can find water to be reduced, or you can find water to be oxidized up here. We're looking at reducing water. That's going to be negative 0.83. And then for F2, this is going to be 2.87. So here's fluorine. The highest potential for reduction is fluorine, F2, and therefore that's the best thing to be oxidized. It's like if you had an analogy that electrons are cookies and you measured everyone's affinity for cookies, how much they wanted them. Fluorine is the cookie monster, right? It lives to eat cookies. So that's how you can think about it. And what's kind of nice, again, with this numerical order is that you have the order for any oxidizing agent in this table. It's going to get stronger as you go towards the top. So if you're comparing or putting things in order, the worst one is lithium plus. Lithium plus down here is allergic to cookies. It doesn't want anything to do with them. And then fluorine is the cookie monster. So you got everything in between. So that's one trick. And then once you kind of get that, there's also really a parallel to acid-base theory with what we did with, conjugate acids and bases, and like the acid strength goes up one way, the base strength goes on the other way. it's the same thing here with reducing agents, because what you want here is the thing that's the best at being oxidized. Best to be oxidized. So instead of looking up a whole new table, which they don't really ever give you for oxidizing reactions, you just have to mentally flip them around. So we'll make these orange. All these species here, right, are things that could be oxidized. And therefore, they're things that could be reducing agents. Reducing agents. All right, and so if I want to find a reducing agent, or find the strongest one, I'm going to look at these on the right side. One thing I would do too, especially with multiple choice questions, is to just eliminate answers. So if I look over here, PB2 plus is on this side, and PB metal is there. So PB2 plus can't be a reducing agent. It's on the wrong side. So I'm going to cross that off, not reducing agent. And then I'm just looking for things on the right side. And then I have gold, which is okay. I have hydrogen gas, which is okay. And I have aluminum, which is down there. So now if I'm going to look at the numbers, what I would really be trying to figure out is the potential to oxidize gold, or the potential to oxidize hydrogen or aluminum. Okay, so if I look at gold, when I oxidize gold, I'm actually flipping this reaction around. So this number now becomes negative 1.5 if I were to reverse the reaction. So that's important to know. This would be negative 1.5. Hydrogen is just 0, so if you flip it around, it's still 0. And then aluminum, if you flip that one around, is 1.66. Right? There's aluminum down there. And so if I look at these numbers, again, these are just kind of telling me the tendency, the affinity for being oxidized. Gold metal is negative, does not want to be oxidized. Hydrogen is kind of in the middle. And then aluminum really does. So aluminum has the highest oxidation potential. So again, these kind of, this list being in order gives you a quick way of doing this, where you can just go from the top to the bottom, and that's going to be stronger reducing agent going down. So it's kind of like, this is where the analogy gets weird, I guess. Fluoride minus is bad at giving away cookies, and then lithium is the best thing. If electrons are cookies, then that really wants to give away cookies, right? It's like the best Girl Scout. Okay, I'm stretching with this analogy, but hopefully you get the idea. So give these things little personalities, might help. Whatever analogy works. Point is to kind of find one, and that will help to reinforce the concepts. So that's good. Next thing would be, does something react with something? Will gold dissolve an acid? Will acid dissolve this metal? Will X oxidize Y? Will Y reduce Z? This question can be asked in a myriad of ways, and it's just the same question of will this thing react with this thing? So what the key thing is that if the overall potential is positive, then the reaction is spontaneous. So yes, it's going to happen. And if the overall potential is negative, then it's not spontaneous, or it's spontaneous in reverse, if you want to say it that way. But that's kind of the whole idea with figuring out if a redox reaction will occur. And what you have to remember with the dissolving an acid thing is that you're going to want to look at this gold metal reacting with acid, which will be H+. So for anything question with acid, it's the main species is H+, as we know. That's our question. Will gold react with H+? Okay, before I show you the shortcut way of doing this, it's best to kind of introduce the more thorough concept, which is take take those two half reactions and see what they add up to. So I'm going to take gold and see if it reacts with H+. So what's going to have to happen to gold is that it's going to be oxidized, because if I'm starting with gold metal, as we said, it can really only be oxidized. There's no reaction that has gold metal plus electrons, or you won't find that on there. So you have this one, which is your oxidation, right? And that potential is negative 1.5, as we said. And then our reduction is going to be H+. So if we look at H+, 2H plus 2 electrons goes to H2. 2H plus 2 electrons goes to H2. That's potential of 0. That one's kind of nice just to remember because it's easy. And again, whenever you have the acid, it's just going to be that one, which is always 0. So we don't even have to really add these, like worry about multiplying and adding them together, because the potentials don't get multiplied. So all we need to do is just add the potentials together. And if we do that, this is negative, which is not going to happen. So that's something I'll point out here is potentials never get multiplied. We'll go over this more in the next video. So even though like to add these two half reactions together, we'd have to even out the electrons, we don't change these numbers. So that makes this pretty nice with doing this, in this quick way. So this is going to be no. Reaction does not happen. It's not spontaneous. Gold won't dissolve. Okay. You can imagine trying this with other metals, and some metals will dissolve in acid because the potential will end up being positive. What I'll point out now is the way I do these involves this kind of shortcut method, which maybe I'll write right here. So when you're doing a question like, does A react with B? Same question as, does A oxidize B? Or does B reduce A? And what you would look for is if you have a scenario where A is somewhere up here on the top part, and then on the left side, and then B is somewhere on the towards the bottom on the right side, or just below A for that matter, then this connection is downhill. And when you do the thing that we did with adding up the potentials, it's going to be positive overall. So this is going to be a yes. That's in contrast with a case where the species A is a weaker oxidizing agent, and B is also a weaker reducing agent. So it's something like this, right? And then when you connect them, it's uphill. This is where I think about gravity and spontaneity. Like A going to B, the ball will roll down the hill, but A going to B this way is not spontaneous. So what's going to have to happen is that the potential is going to be negative, and it's going to be no. Again, I'll emphasize this, the potentials have to be in numerical order. Otherwise, this trick does not work. So bear that in mind. With any kind of shortcut, you have to be aware of kind of the limitations. And sometimes on an exam, maybe they'll give you a table where they're not in order, just to make it a little more difficult. Then you have to do what we did before with the actual numbers. But just to kind of show you, again, like taking H plus and gold, that's uphill. I can just look at this table and say, no, those two will not react together. Whereas, does nickel dissolve in acid? Okay, so now I take H plus, I take nickel, that's downhill, that's going to be yes. I just know that from looking at this. So kind of a cool trick, right? I think it's again nice, but better to understand the underlying concept and the knowing how to write the half reactions if you need to. So to wrap this all up, this trick is especially good for this question, which is, can be somewhat complicated if you're trying to just do them with all the different half reactions and different combinations. Which species can oxidize lead but not chloride? Okay, so we're looking for an oxidizing agent. That, again, might be a way to eliminate something. In this case, F- is not an oxidizing agent. Because if you want to oxidize lead, then the thing you're picking has to be reduced, or has to be an oxidizing agent. So on this table, F- is on the wrong side. It's on the right side up here. I guess I should say it's on the product side. It's not the correct side, right? Okay. So what I want is something to react with lead, but not chloride. So what I can do is I can look at those two species. Here's lead, here is chloride, right? Okay, so the choices I have are, and again, if I want to kind of write this out in with the numerical values, which is probably good. To oxidize lead, we have a potential of 0.13 positive, and to oxidize chloride, we have a potential of negative 1.36. So doing this kind of fast, but you can get these numbers from the table. Okay, so if I choose lithium plus, the potential to reduce lithium plus is, write that down. It's negative, this reduction potential, negative 3.05. So the problem with lithium plus is that if you put that with these, it can't do either of them, right? So that's the worst oxidizing agent. Here's lithium plus. That's going to be uphill for both of them. That's going to be nope, both of them. Then I have, let's look at gold 3 plus. So gold 3 plus, the reduction potential is 1.5. So if I take gold and put it with both of these, it's going to actually be overall positive with both of those. So the reason gold is not our answer is that gold 3 plus is a good enough oxidizing agent to oxidize both of them. Right? Just think about this here. I circle gold 3 plus. Oh, that's downhill for chloride. It's downhill for lead. It will be able to oxidize both of them, right? Gold loves cookies, a lot, so it's going to take cookies from both of them. It's going to steal cookies from both of those other ones. And then hydrogen is our answer because this potential, remember, is 0. So if you put it with, if you put this with that, that's going to be positive. If you put 0 with this one, that's going to end up negative. So that will not be able to react with chloride. And again, just the quick way, like on an exam, I would just find the one that's in between, because then you have, the no. So anything in between those two, lead and chloride, there's actually a lot of choices here that would work, like iodine or Br2, bromine. Though anything in the middle here basically would work to oxidize one and not the other one. All right, hopefully that makes sense. And just let me know if you have any questions. And I think with this trick especially, once you practice a little bit, it gets easy, and then it's just a nice way to do it. Just make sure they're in order of the number, and I'll leave you with that and talk to you later.